and welcome to our talk about deterministic size discovery and topology recognition in radio networks with short labels. I'm Adam Gańczosz, and this is a joint work with Tomasz Judziński, Mateusz Lepko, and Andrzej Belc. We will work in ad hoc radio network model. Here we have a graph G, where we think of each node as some kind of computer, and edges determine which two nodes can communicate between them. If there is an edge between two nodes, that means that they can communicate. In each node can do such things. First, it can either transmit a message or listen to incoming messages. And after that, it can do any kind of local computations. We do not want to bound this computation in any kind. It can do anything that is computable. The node will receive a message if and only if it listens and exactly one of its neighbors transmits. Well, if none of the neighbors transmit, then it just hears silence. And if more than one neighbors transmit, we also does not receive a message, and it's something we call a collision. There are two versions of this model. First, with collision detection, that is, when machine can distinguish between the state of the silence and the state of collision, and without collision detection, that is, when machine cannot distinguish between them. Okay, for the motivation of this filter, we know that for deterministic algorithm, we must often assume that we give each node some unique IDs. That means that for each node, we give some kind of label of length at least logarithmic in size of the networks. On the other hand, there are randomized algorithms, which does not need any kind of labels. They can, for example, just choose ID at random at first. But for the case of deterministic algorithms, we know that there are some problems for which it is impossible to solve them without some kind of labels. The example would be a task of broadcasting, where we have some source node which has some kind of message and want to broadcast it to the whole graph. We know that, for example, for the graph shown here, it is impossible to solve this broadcast deterministically. Because when this source node broadcasts its message, both of its neighbors will have the same state, and they cannot distinguish between them which one would just broadcast in the next round. So due to the problem of symmetry breaking, it is impossible to solve this broadcast. So natural question arises: what is the shortest possible label for some problems? To answer this question, there was an earlier framework introduced. This framework consists of two parts. First, a labeling algorithm, which is some kind of oracle, which has full knowledge of a graph, and assign each node a label. And then we have a distributed algorithm, which tries to solve this problem using only this given label. With this framework, we tried to solve two problems. Firstly, the problem of size discovery and the problem of topology recognition. But before I will talk about our results, first I want to talk about another problem, which we will be using as a black box in our results. So this problem is a broadcast problem, and it's a very easy problem. We have some chosen node S called source node, and it's given a message M. The goal is for each node in this graph to learn this message M. And this problem was researched earlier by Allen and Gilbert, and they showed an algorithm and labeling scheme where labeling scheme is of constant length, and algorithm runs in time roughly d times log n, d being the diameter of the graph. Okay, so for our results, the first result is a result for the size discovery problem. And size discovery problem is a problem where every node in the graph must just learn its size. That is the number of vertices. This problem was earlier researched by Gorain and Peltz. What they did, they showed an algorithm which uses labelings of size log delta. And also they showed that this label length is optimal. However, they firstly assumed collision detection, and this result relied on this collision detection. And also they had quite a big time. That means it was clearly greater than linear in size of the network. As for our result, we did firstly an algorithm which does not use collision detection, still using this optimal label length, but with time only log squared n. Then we showed that this time is optimal for our labels length. First, I will talk about algorithm for size discovery. And this algorithm consists of two parts for two distinct cases. First, we will talk about low diameter graphs, that is when diameter is O log n. And then we will talk about high diameter graphs. For the case of the low diameter graphs, firstly, we showed an auxiliary result that there is a subtree with small degree, that is log delta, but which is big enough that it has at least log n vertices. That enabled us to encode n just in the nodes of this tree, and then we can just gather these encodings in NS, and S will broadcast this value of n in the whole graph. Time of gathering can be just the degree of this tree times diameter of tree, that is log delta times log n. And the time of broadcast also is this log n times diameter, so log n times log n. That means that this part runs in only log squared n time. For the case of high diameter graphs, we firstly partition the graph into clusters of diameter roughly log n. And in each cluster, in parallel, we will do following things. Firstly, in each such cluster, we will choose a shortest path, P, of length approximately log n. And this path is shown on the picture as this blue path. Then we can encode the bits of n just using constant number of bits in each node on this path. Then we can gather all these encodings in S and rebroadcast them in a whole cluster. Still, this gathering uses roughly log n time, and this gathering also is in clusters which have diameter log n. So the whole broadcasting and gathering and full part of the algorithms runs in time log squared n. We also showed a lower bound on time for size discovery. And we did it by showing that the existence of size learning algorithm with time smaller than log squared n, with labels smaller even than log n, implies the existence of broadcasting schedule of length smaller than log squared n. And this is a direct contradiction with known result by Alan Barnoy, Linia, and Pelek, which states that that all broadcasting schedules needs at least log squared n time. The second problem we talked about was the problem of topology recognition. In that problem, we want for every node V of our graph G to output two things. Firstly, some kind of graph G prime, and the node from this graph G prime, such that this G prime is isomorphic to G, and V prime corresponds to V in G. What we did for topology recognition, we did two things. Firstly, an algorithm with labels of size log delta and time roughly d times delta. And then we showed that our labels length is optimal. That is, we showed a lower bound log delta on the size of the labels. For the algorithm for topology recognition, firstly, we fix a BFS tree and some kind of two-distance coloring of vertices. Then, by simple broadcast, each node can learn its unique ID, which will be concatenation of its color and the colors of all its ancestors. And for example, we have shown what would be the color of the node lowest on this path. With unique IDs, we can use the round robin on colors from two-distance coloring, so that each node will learn unique IDs of all of its neighbors. These kinds of neighborhoods we can then just collect in some source node, and using this knowledge, it can reconstruct the result, which will be rebroadcasted to all nodes in the graph. What we did then was a lower bound for topology recognition, and we showed that for each delta, we can build a graph, a G delta, such that for each assignment of labels, lambda of length smaller than log delta, and for each algorithm A using this lambda, there will be two vertices of different degree in G delta with the same state, which will be indistinguishable. However, for the topology recognition, we need at the end of the algorithm for these two vertices to output different answers. That means that this algorithm A cannot be algorithm for topology recognition. To conclude, we showed an algorithm which uses optimal labels of length log delta with time log squared n. We also showed that our time for size discovery is optimal. Then we also showed an algorithm for topology recognition with size of labels log delta and time roughly d delta, and we showed that our labels length are optimal. There still remain some open problems. Firstly, we do not know whether our time for topology recognition is optimal. We suspect that it isn't. We suspect that there is some kind of trade-off between the size of the labels and the time of the algorithm for size discovery. And also, there are not many papers on this model, so there are still many problems for which we do not know optimal length of the labels. And that is all. Thank you for listening.